We're going to talk about ionic compounds, and today I'm the one with the document on camera. So these are all legitimate ionic compounds, and so with this list, we are going to come up with some rules on the naming of ionic compounds, perhaps any important observations about ionic compounds, and how the chemical formula works.
Are ionic compounds, and they come from, they're made up of metals here on the left-hand side of the periodic table, bonded to non-metals on the right-hand side of the periodic table. Right. This is the periodic table that's in the Cengage mine tap, so it'll be one that people see relatively frequently.
Mm-hmm.
So we've got metals on the left, non-metals on the right, and those form ionic compounds.
Yeah, so exactly like Dr. Hunter mentioned, that these compounds are made up of one metal and one non-metal. And it's actually pretty convenient how the metals are on the left and the non-metals are on the right in the formula on the periodic table and how you name the compound. So I'll type that out right now. Ionic compounds are made up of metals and non-metals. Okay. We have this interesting thing in some of these names. I don't know if you've noticed, but for copper bromide, there's a Roman numeral 1.
Right.
Then in copper sulfide, there's a Roman numeral 2. And in cobalt, there's a 2. But in some of these, there are not any Roman numerals. And you might be wondering why that might be the case.
I've got a question.
Mm-hmm.
How come some of those compounds have Roman numerals?
Yeah, exactly. So, you could refer to a periodic table, but I'll just discuss it here right now. That copper and cobalt, those are what we call transition metals on the periodic table. They are not, they're in that block in the center of elements that honestly, as an organic chemist currently, we don't use too often. Yeah. But they are transition metals and they signify something. We don't know what it is currently. These transition metals seem to have Roman numerals, whereas these metals that are on the very left column on the groups we call alkali metals and alkali earth metals, those do not have Roman numerals.
Okay.
Transition metals have Roman numerals in their ionic compound name versus the alkali metals do not have Roman numerals in their ionic compound name. So we'll explore what the Roman numerals might mean. And give me 1 second.
There we go. Cool.
Yeah. So we have this periodic table, and here I'll circle around what the second rule that I last mentioned. Okay. So copper, Cu. Cu is right there. We have cobalt, and we have cobalt right there. And this middle block, the one I'm kind of
Yeah.
making a rectangle around, are called transition metals,
Right.
and they have the Roman numerals. But these metals on the further left do not have any of the Roman numerals, like lithium. Lithium does not. Potassium does not.
Okay.
And so looking at the periodic table might give us a hint as to why the transition metals have Roman numerals. And so if you know what ions are, they are atoms of an element with more or less electrons. And so one ion is attracted to another ion. So I will write out those rules below, which explain why they're Roman numerals. First, ions are elements with fewer or more electrons than usual, I suppose. And because electrons, as we know, are negatively charged, if you have more electrons than usual, then that would mean you're going to be more negative. And then the opposite, if you have less electrons, you're going to be positive. So, getting back to the idea of the Roman numerals, perhaps you'll already know this, perhaps you won't, but these metals in the first group right here, they all have one valence electron. And because of that, they typically form ions that get rid of that one electron. So that means that they are positively charged. And having one less electron means they are positively charged by 1. And that is the same for all of these elements in this group. And you can say the same thing. And the second group has a similar pattern where they have 2 valence electrons. And they tend to make ions that get rid of those valence electrons. So less electrons, less negative, more positive. These ions are going to be positive, and having 2 less electrons will make them +2 charged. And so, because these elements always have the same ionic charges, they don't have Roman numerals. But when we get to the transition metals, and perhaps you'll understand electron configuration, orbitals, and stuff of that nature already, these elements have a lot of valence electrons that they can get rid of because they have the d orbital, or they have more space to hold more electrons. So copper, as you can see up above, it can be copper 1 or copper 2. That signifies whether it lost 1 electron or whether it lost 2 electrons, and so on. And there are many of these transition elements that have many differently charged ions. And so this positive charge is important in ionic bonding because the charge needs to be balanced out by the charges by the nonmetals. So let's recap what we have so far. We know that metals are positively charged ions because they lose electrons. I also forgot to mention we have specific names for differently charged ions. A positively charged ion is called a cation. Positively charged. Nonmetals are negatively charged. I guess I'm getting a little ahead, but ions because they gain electrons. And so these elements on the right, the nonmetals, they have a lot more valence electrons. In this group right here, they have 7. In this group over here, they have 6 valence electrons. And it's a lot harder for them to get rid of their valence electrons. So they'd rather just gain 1 or 2 electrons to fill up their octet or to be in a more stable position than having 7 or 6 electrons. And so that's why they like to gain electrons. And so since the metals lose electrons and the nonmetals gain electrons, that's why it all works out when they bond together to make ionic compounds.
So we could say metal cations are attracted to or bonded to non-metal anions.
Yes, an anion is the negatively charged ion.
Right. So in that, what's the first example you're showing there at the top of the screen? I can't quite see it. So we've got calcium iodide, right? So we have calcium iodide, CaI2, and one of the things that we know is that calcium comes from group 2 of the periodic table, and so we know that that forms calcium, an ion with a 2+ charge, right?
Yep.
And iodine comes from group 7 in the periodic table. And so it forms iodine with a single negative charge, right?
Mm-hmm.
And so to balance out these 2 charges, we have 1 calcium at +2. We need a second iodine at -1. And so calcium iodide is formed when we have 1 calcium cation bonded to 2 iodide anions. So we get the formula CaI2, just like it showed in your chart.
Yep.
And it's important to know that in this case, if I had a third iodine with a third negative charge, now my charges wouldn't balance out. And so it won't form calcium iodide with 1 calcium and 2 iodine, or sorry, 1 calcium with 3 iodines, because that wouldn't balance out. And so the only way we can make this compound, the only way nature makes this compound, is by saying, by assembling 1 calcium and 2 iodines. And so if I say calcium iodide, I am saying 1 calcium, 2 iodines. There is no doubt about whether or not there might be a third or a fourth iodine. And so we don't have to have the prefixes that we've seen in other places.
Yeah, such as in covalent bonding.
So in this case, we have, all we have to do is say calcium iodide, and we know that means, oh, calcium iodide. That's what calcium with a 2+ charge, iodine with a -1 charge. There must be 2 iodine anions to balance it out.
Mm-hmm.
I'm going to just go back to the periodic table here for a second. So over here on the left is calcium. Calcium is in group 2, and so it forms a 2+ charge. Iodine is over here on the right-hand side in group 7. That if we don't know already, soon that will remind us that it forms a -1 charge, like all the other elements in group 7. And so that's how we end up with calcium 2+ and iodine 1-.
Yep.
What was the next one that you had on your list?
The next one I had was lithium fluoride.
So lithium fluoride. And I think the formula for lithium fluoride is LiF. Is that correct?
Correct.
Okay. So let's go back to the periodic table again and see if we can make sense of that. So here is periodic table. Lithium, Li, is over here on the left-hand side. It's in group number 1. And so that tells me that lithium forms a 1+ ion, and fluoride is over here in group number 7. And so that tells us that it forms a 1- ion. So that was lithium, which came from group 1, and fluoride, which came from group 7. That tells us that it's lithium with a 1+ charge. This tells us that it's fluorine with a -1 charge. To get those charges to balance, 1 lithium and 1 fluorine work for us, and so we can write lithium fluoride as a compound.
Yep.
And we'll never have 2 lithiums bonded to 1 fluorine, so we don't need to say dilithium fluoride or trilithium fluoride or anything like that. Lithium fluoride, you said it all.
Yep. How about one of these other compounds we could do? What about copper 2 sulfide?
Okay. Copper 2 sulfide. Okay. So let's go back to the periodic table again. So here's copper in group 1b, group 11, and it's in the transition metals, just as you said. That means it can have a variety of different charges, which is why in the example you've given, it's told us copper 2. And so that tells us that it must be the copper with a 2+ charge. Sulfide is from sulfur. It's in group 6, and those form a -2 charge. So we're going to do copper 1 and sulfur sulfide -2. So copper copper 2 tells us that it's the copper with a 2+ charge. Sulfur with a 2- charge. This Roman numeral 2 told us that this is 2+. Sulfide from group 6. And that tells us that it's sulfur with a 2- charge. Fair enough?
Fair enough.
Okay, so +2, -2, those charges balance out nicely. And so the formula for copper sulfide is CuS.
That looks good enough. That looks
Yeah.
perfect.
Oh, thank you. Should we do one more?
I think I understand the concept. Should we do another one?
Let's do one more. Let's do one more.
All right.
What else? What's the hardest one you got on your list?
We can do potassium oxide.
Okay. Potassium oxide. All right. The thing I know is that potassium has a symbol of K and oxygen has a symbol of O.
Would you like to know the groups they're in, or are you going to pull that up?
I'm gonna bring up the periodic table and show it right here. Okay, so I see K for potassium over here on the left in group number 1. So that means potassium has a 1+ charge. And oxygen is in group number 6. And that means it has a -2 charge. I'm going to stop the sharing there. So potassium, group number 1. And so it has a +1 charge. Oxygen is in group 6. And so it has a -2 charge. I put them together, and if I have 1 potassium and 1 oxygen, overall I'm going to have a -1 charge. So I need a second potassium. So now I have 2 positive charges and 2 negative charges. And so that tells me that in my formula, I have to have one potassium, 2 potassiums, and a single oxygen. And so the formula for potassium oxide is K2O.
Yep, that's correct.
So that's one of the ways in which we use the periodic table to identify the groups that the elements are in, and to help write and based on what group they're in, we know something about the charges they form, and then that helps us to write the formula for the compound. Ionic compounds. They're ionic compounds because they form ions, and those ions are formed by metals bonded to nonmetals. The metals form positively charged ions, the nonmetals form negatively charged ions, right?
Correct.
Occasionally we're going to see some Roman numerals in there, and those Roman numerals are from those elements that are transition metals, and the Roman numerals tell us something about the charges on those transition metals. Alkali metals and alkali earths don't have Roman numerals. They have very specific charges that are related to the group number and the structure of the atoms. Group 1 forms +1 charge. Group 2 forms +2. And over on the other side of the periodic table, group 7 forms -1. Group 6 forms -2.
Yep, and you just covered that with that last rule too.
Right. Yeah, because when atoms lose electrons, they are internally unbalanced, and so they have a positive or negative charge, and those positive or negative charges can be attracted to each other. Here's group 1 losing, become positive, having a positive 1 charge. Group 2 has 2 valence electrons, and so they lose 2 electrons and result in a positive 2 charge. Transition metals can have many valence electrons. I'm not sure that we ever said that what a valence electron was, but let's just operate on the assumption right now that a valence electron is an electron on the very outside of an atom, and it's possible to lose those electrons or to bring other electrons in near those. So copper can, these transition metals have many valence electrons, and so copper can form +1 or +2, cobalt can form +1 or +2, and lots of the other transition metals can all have a variety of charges. The positively charged ion gets a special name. It's called a cation, and a negatively charged ion gets a special name called an anion, right? The way that some people remember this is that in the middle of the word cation, there's a T, and in the middle of the word anion, there's an N for negative. So that might help people remember. The T for the plus of the positive, and the N go together for the negative for the anion. And then once something has a positive charge and a negative charge, they can be attracted to each other to form a compound.
Yep, that sounds good.
So what else should we add to this? Anything?
It's pretty difficult at first. You don't really remember off the top of your head which elements are in which groups and what charges they have, but make sure to always refer back to the periodic table. It is your friend, and to always balance out the charges correctly.
Yeah, certainly. Yeah, the periodic table is your friend. It has a lot of information that's just waiting for you, and you're not expected to memorize the periodic table, but you are expected to be able to use the periodic table to solve some of these problems. So, thank you, Kevin.
Thank you, Dr. Hunter.